Just quick hand. Anyone involved with ML here? Like anyone that were? Okay, great, fantastic, fantastic. So yeah, so I'm Mutsatefe. I'm just trying to. I was trying to teach myself this stuff a few years. I work in a company that deals with like low latency serving for ads, unfortunately, and I've seen many iterations of products along the years, past like 7 years. Um, you know, it never stops improving or getting worse. But here, I try to really write down kind of what the internet thinks is ML latency techniques, reduction techniques. So let's dive into it, right? So the first PSA that I want to leave you with is that you want to focus on the latency of your ML models. If you are serving ML models live to some customers, that's the first thing that they're gonna see. And the many teams forget this PSA, and then they discover too late that their models are not responding fast enough, and so you lost 6 months of valuable time. So what will you get from this talk? This talk, first, I want you to understand, low latency real time, what kind of options you have, and just a map of thinking about it. You get to sound smart with your product managers. You get to save yourself time. You don't lose hope when engineering comes and tells you, we can't help you deploy this because it's too slow, and your product might succeed. Who knows? So I tried to put this in pictures, right? I think most, like generalization, like very visual people. I have like 2 maps. One is the data flow patterns that I've seen happening over the years, and then common abstraction layers. So this is on my blog post. I have a blog post about this. We're just gonna go down the list just to motivate you to read it or to look at the references. I don't expect you to, remember everything I've said today. So, mostly just enjoy the flow. Just get a sense of what's happening over the. So basically, what do we say? We have the not so rare case of excessive ML latency. So things that can, they're like symptoms of low latency ML use cases is that the cutoff is really like 100 milliseconds. Everything above it is offline. I call it offline. So 100 milliseconds below, humans, consumption of information really, if something takes longer than 100 milliseconds, for some reason, they lose interest. So you lost the customer. So that's like the core kind of idea there. During the optimization of this, you need to learn this nice concept of optimizing versus satisficing metric, optimization. You need to realize that you're going to be dealing with like low latency read databases a lot. And then we're going to talk about pre-computing and caching tooling. Okay. So the common abstraction layers that I found so far, not that I found, that I collected so far, is really this tree of information. So we are here, right? ML latency. We're gonna go down this little tree of knowledge together. So first thing that data scientists, whenever they join, year 1, month 1, is like they learn that their training. I don't say like their training, but like 80% of their training is based on this pipeline. This pipeline is you have a data warehouse, you have some pre-processing jobs, you pre-process the data to make it consumable by the scoring jobs, and then you store the scored data and you make it available in some sort of database that consumers can hit whenever they need. But those consumers expect a database response. They don't expect a low latency ML systems. So this is like 80% of the training that data scientists get. But in the online world, right, it's like you have this real-time generation of recommendations, online ranking, predicting if a critical piece of equipment will fail, sharp medical devices that are like, doing like knee surgery you really want to be quick to detect problems. Grocery time. So inside the online world, you have two types, right? You have the synchronous, asynchronous. Asynchronous is divided in two parts, right? I don't know what happened to my pictures, but it doesn't matter. They're a little bit, sick. So you have push and pull, right? So like when you are having asynchronous interaction, you have two ways. Either you push in information, so the caller goes like, hey, I have this logged in user. She's she's currently active, but messing with her subscription settings. Should we send her a new retention promotion email before she quits our amazing service? Model say, let me think about it. I'll send you a push notification if we need to. Then you wait, time passes, and then the caller says, send this promotion for 3 free meals. This is the push method. The pull method is the caller itself is, hey, I have this logged in user, let me think about it, and then the caller is like, any news? Okay, let's incentivize them. So those in the asynchronous world. Asynchronous pipelines, if I had to summarize it, right? It's a little bit too much, but you have a client up top. It hits a prediction API submits stuff to request events. There is some event processing, and it hits an event scoring system, passes the scored events back to some messaging system, and then you have two options to collect information and give it back to the client. So this is asynchronous. Like you don't expect too much trouble. But when you are like dealing with synchronous online prediction, that's when the pain kind of really shows up. And it shows up because now you have the ML API is a REST API, gRPC, some sort of API that you expect it to respond right away in like less than 10 milliseconds, for example. And the model generates prediction, sends it back to the caller. And if you run out of latency budget, then you say to the customer, prediction took too long, try later, we lost the customer, right? So you have this concept of timeout that's just that's your budget. That's how long you're willing to wait. But it's almost like the performance profile of this synchronous apps. Sometimes, new data scientists, they think that it's just the model, but in fact, it's you have pre-processing of enriching the input request, generating the prediction, post-processing, and then you have a bunch of security encoding that slows down the traffic, load balancing, auto-scaling number of components. It's lots of fun. So how do we deal with this synchronous world, right? So we're here, right? So synchronous predictions. The big thing that's nice to keep in mind for synchronous is that you can split them into two parts, right? You split them into the construction of the prediction and the serving of the prediction. And the big realization, and lots of ML engineers get right away, is that only so much can be done to optimize the model, right? You can remove supporting components, you can mess with core components, but so getting rid of supported model components is like the first thing that happens. Like, oh, I have extra logging, extra metrics monitoring, debugging helpers. All that goes away, right? You can remove them as long as you have some testing embedded in the code, so you know that you didn't break anything. But the real key to optimize this sort of systems is realizing that you are not just in the optimization offline world where you're optimizing some sort of like, map, MRR, accuracy, precision, log loss. Those metrics are great in the offline world, and any new, higher high, lower lows are great when in the offline world. But you need to realize that you have a satisficing metric that you need to take care of. Is will it fit in the model? Will the model fit in the device that's at the edge? Or do I require special chips? Can the feature processing finish within time bounds? And then the model latency, of course. So you know, like you see people, you see, you know, newcomers focusing on optimizing metrics. So you end up ignoring the satisficing metric. So satisfying metrics, some things like if you want to speed up latency of your model at the model construction, at the prediction construction part, what you do, you can specify a smaller model, you can have a lower number of features, you can do sparsify when possible on the model itself, you can trim the number of trees, you can trim the number of trees in a random forest, in gradient boosting trees, you know, smaller layers in a neural network, smaller number of variables in a logistic regression. But all of this needs some sort of method. So the method that you want to use is that you set the satisfying metric to something that's business related. Our customers will give up on our product and go to our competitor if we don't serve this prediction with less than 10 milliseconds, for example. And then you keep increasing the complexity of the model, which hopefully increases the, you know, the evaluation metric that you're using until you get really close to the satisficing metric. Again, so if you have two options, if the model latency meets the requirement, but the predictive effectiveness is too low, you keep increasing the complexity. But if the model latency is too high, then you need to, you know, it's like a, and you can't achieve the predictive requirement, then it's a business kind of decision. Like you can't really, the business needs to adapt. You cannot force a business to use a slow model just because offline is great. So that's something, that's a nice little method of doing it. So the second PSA is that you want to realize that 10% model local latency construction boost will get crushed by distributed I/O. So as soon as you think that, you know, your local laptop model or, you know, whatever training infrastructure you're using is great. Oh yeah, like I can do, you know, 2 milliseconds, whatever, like improvement to my model. As soon as you're gonna hit distributed I/O, you're gonna run into trouble. So why are you gonna hit distributed I/O, right? So it's in the serving part. So we looked at the construction part, but in the serving part, you have two parts. You have the model inputs, model outputs, right? So the features in the model inputs are pretty much the whole operation, the whole time sink that you're gonna have to deal with, right? So they come in three flavors. This is like part of the mental model that I try to keep in mind. You have user split features, static reference features, and then dynamic real-time features. You know, some things come directly from the request. Some things are like historical values that you can pre-calculate, and then dynamic real-time features like what did the customer do in the past 5 minutes. So the easy case, right? The easy case is when you have every ML gateway around will be asking for this sort of query. I need a single row with one column for each of the features of entity X. So you have this usage optimization, but then I guess the third realization is that newcomers, they're like, okay, I have this great data warehouse, you know, terabytes of data are loaded in there. I can do aggregations, build my training sets, everything's great. But at serving time, the latency for data warehouses, that's not what you want, right? So that ends up being so you're a data scientist at a large corporation or like a small startup, and then you have to do this, right? So periodically extract the simple and aggregated features and place them in a data store optimized for single key lookup operation. So that immediately slows you down, I mean, in terms of product development, because you have to talk to some external team, like a data engineering team, that will help you do this, because it's not in your core competencies. So you want to budget for that time in terms of development. But what does it look like in a picture, right? So in a picture, you start seeing that there's going to be two things happening separately. In the offline world, right, we have the data warehouse feature set, and then you have these batch jobs that are going to be crucial to your success. and there you're gonna load them in a low latency static feature storage. And now the ML gateway becomes kind of critical because it is responsible for getting a client entity ID or like a customer ID, looking up the attributes for this entity, static features that we have, and then giving it to the ML model for scoring, and then returning it to the client. So it's a little bit of a dance. This ML gateway becomes more and more important for your latency requirements. Overall, still feasible, right? Still feasible. So the less easy case in dynamic real-time features is when you are trying to use not historical averages or historical stats. What you want is like what happened in the past few kind of, few interactions with your product, or you have some sort of warehouse with machinery that's making some cookies, and you're like, which one where's the butter is gonna melt too quickly and it's gonna start a fire. And so you're collecting information pretty quickly. So in this next diagram, you have two inputs. You have the events up top, and then you have the clients that are trying to get a prediction on the bottom. So the core part of this machinery is that now you're gonna have the events come in. So that's like the time series that are happening or sorts of events that are happening. They're gonna come in an event processing system. Event processing system is gonna try to do real-time feature engineering, feature transformation, and then store the features themselves in a low latency feature store. And at the same time, as soon as there is new data, enough data to make a prediction, the model API is gonna get involved. So you are pre-calculating the model, the predictions, and storing them in some output database. And what happens is that the ML gateway now is constantly waiting for a request from the client, and that's you pick up the predictions from the read low latency read prediction store, and return them to the client. And then you don't live in an isolated world, so you're like, I need to also publish it to some downstream consumers of this thing in another messaging system. So it gets a little bit more complicated, right? We have messaging systems, we have event processing, low latency for features, and low latency for predictions. It's a little bit strange. So this is just how I describe what just happened. So that's for the model inputs, right? Model inputs, you have this branch here where you can handle various strategies. On the bottom side, you have model outputs. What do you do with model outputs? So once you have a prediction, right? If all the techniques covered so far do not make your prediction latency low enough, then you need to pre-compute and cache the predictions. To do that, the basic flow, right? The basic flow is the same, right? You have a client up top, ML gateway, and ML gateway just expects the predictions to be already pre-calculated. And on the bottom side, or you have offline data, batch processing, prediction outputs, and periodic updates. So what kind of challenges do you face there when you try to pre-compute your predictions? Is that you have a problem with lookup keys. So lookup keys become critical. If either you're in a use case where entities are okay, right? You have a domain entity, or you need to rely on a combination of feature values, things like location, current shopping cart, segment information, product category, things that are going to be more anonymous, which is sometimes required, and you need to specify what's this feature combination look like, right? So you're stuck, right? You're stuck with dealing with this entity cardinality. So if you have hundreds of vehicles that you're monitoring and want to predict, which truck is going to break down, we need to stop it or whatever, you have hundreds of vehicles. But if you're like 100 million catalog that you're trying to run recommendations on, the entities cardinality just blows up. So how do you deal with this, right? So instead of calculating predictions for all the entities, what you're gonna do is you're gonna run top n kind of most blank entities, right? So most interacted with, most viewed, most some sort of verb that matters for your business. And then you pray for the rest of the long tail of remaining products. So what happens here is that, again, you have same story, right? You have the client up top that talks to a model gateway, right? Model gateway checks for the top n entities and an in-memory output prediction. So like, do we have any predictions for this user, for this entity? If we don't have, then it checks the non-frequent entities in a I guess less expensive database kind of where you can store more entities but cheaper. And then if none of those work, then you go for the you run a live prediction on your model. Again, from the bottom, same kind of story. You have batch scoring jobs, and then batch training job that uploads models or uploads pre-calculated predictions. So that's for how you do pre-computing the predictions. But remember, this is just an example, right? You have a combination of values, right? Like country, device type, song category. You really want to think about it's the product of those. So you really want to say, I'm going to set a cutoff on the top most useful items that I want to predict on. Okay, so it's just I guess the key here is that as you're discovering this domain of low latency ML, you see there's like these jumps in pricing of the databases that you're going to be using, or the sort of low latency APIs for querying and pushing data. There's like little jumps, right? Like I guess like every cloud provider provides almost like this 3-tier. I don't know why it's like three tier, right? You have like the cold storage sort of, we will return to you data whenever we can. Then you have the ones that are disk based, but they say they are low latency, and then you have in-memory kind of storage, and then that's like the lowest latency you can get, and then here the joke is that the financial operations are going to come to you. They're going to be like, oh, your bill last month was too high. So what do you do again? Is not only now you solve somehow the latency problem, but you use the same algorithm between optimizing and satisficing metric to lower your cost as well. So the cost of your infrastructure, and so how do you do that, right? So you want to reuse predictions as efficiently as possible. We're here now, right? We're here. So to reuse prediction, you have two methods, right? You have exact match, and you have approximate matching. Exact match is like, I have this product. What are the products that are closest to this product? But I need to return them to the customer as quickly as possible. So that's exact matching, like But then you have approximate matching that will do something special, right? It's a bit of a, I guess, still a research topic in the ML sort of research, is that you're able to build these embeddings of the products that are features that represent the product, but they keep the distance between products. So any sort of semantic distance between two products will be kept if they are in the real world space close to each other. Those vectors, those embedding vectors that you generate, will be close in the embedding space as well. Huge discovery. It's like pretty impressive. But what you do with those embeddings is that you drop them in a database where you can build an index on these vectors. There's a couple examples. The annoy system or scan-n are two popular ones. But here what you need to realize is that you have a model that, so you have your products in your data warehouse, right? You build embeddings from that, and then you build an index on those products embeddings. But then at request time, you use the same model to generate the entity embeddings. So that also needs to be optimized so that you can calculate the embeddings pretty quickly. The main concern that happens is like, oh, you know, what do I do if the index is too large? Just, you know, you cannot search fast enough. You cannot search fast enough, so you reduce the embedding size to get a smaller index. If you can't get the right mix of optimizing, satisficing trade-off, you just look elsewhere. Okay. Other tips for low latency caching of predictions, you have things like you definitely want to realize that you're going to have more rows than columns. And you have, if you have high categories, high number of categories, high cardinality categories, then you're going to have a bad lookup latency for your features. And obviously, bucktizing, you know, is going to be part of your, that's all you can do, really. So the main method, again, you lower the cardinality and the satisficing metric is okay, and the optimizing metric doesn't whine too much. Overall, the summary of this, again, is to just give you like an overview, right? Pretty quick overview of what are the options available today. Probably, you know, most of them, obviously not all of them, but just most options, right? It's like the work of an ML engineer or a data scientist, probably I'd say 60 to 70%, 80% of the time is going to be in the offline world. And so don't get too complacent there. In the continuous delivery kind of aspect of our work, you do want to start with they call it a primitive whole, right? A primitive whole system, where you know, it's not quite a full-on system that you want, but you went all the way from your experimentation to the serving and back, no matter how bad your offline metric is, as early as possible in the product life cycle. You know, just reporting like personal drama. You know, you keep stuff on your laptop and you're helping data scientists, you know, optimize. But then as soon as you hit serving, you realize that it's a completely different world. So what you really want to use those continuous delivery sort of ideas where you go all the way, you know, commit, acceptance, performance, conformance, you know, governance, and you're at the point where you're able to simulate real traffic from the real product that you're going to be serving without waiting too long, right? Then you sound smart, save yourself time, and then so you know, these two maps are pretty useful. The first map that we discussed, right? We went from the offline one, number one, you know, and then you have the async version, and then you move into the synchronous world, where you're going to split this sort of offline online, and then you have the real time events processing as they come in, and then you have what kind of strategies you can use for the caching and pre-computation. I have more detail on my blog post if you want. And then this nice map, right? It's nice to keep it in mind, right? This is bang for your buck on this side, and then common abstraction layers. We start and see, split it offline, online. You know, if you need synchronous, you need to split it again, construction or serving, and then I guess I can't like beating a dead horse, but just don't get stuck here. You know, don't get stuck in the construction for too long. You definitely want to test out your latency early on in your product lifecycle. Then you have two types, like model input, model outputs. The approximate matching is still ongoing research. So it's kind of nice to see that people are going to come up with new ideas. There is one here that I didn't cover, the authoring and discovering. It is not, you know, sometimes DNS is like a good example of like discovering which feature you should be using will add to your latency. So you definitely want to have some optimization there. That's pretty much it. So I have a couple links here, blog posts, sort of architecture stuff. There's a couple blog posts that I wrote about feature stores if you're interested. More DA posts, and I have a little book here that I wrote 2 years ago, Clean Machine Learning Code. That's more about like, code quality. But yeah, thank you for your attention.
All right, thank you, Musa. Do we have any questions? I'm going to come back there with the mic.
Thank you so much for sharing all this. It's a space that I'm still learning more about. What I'm curious about is there ever an approach where your model that you trust the most and is most accurate? I'm referring to the the caching, but then the cache misses and so forth. And so, do you ever see an approach where you have your best model, but maybe the slower one? And if it's a cache miss, then of course you keep track of, okay, maybe we need to cache that kind of thing in the future. But for now, we'll use like a faster model that's like, it's not quite as good, but it's faster. Is that an approach that you see sometimes?
Correct. Yeah, we've seen. Yeah, you've seen. It's like you're collecting information about which. So yes, like this diagram here. Let me find this. Yeah, so this diagram here, where you're checking for your cached, super fast, super duper fast here, and if you don't find them, but you notice that you're getting the same sort of entity or feature combo again, right? That's part of collecting information about what kind of prediction requests are you getting, and then you keep them somewhere, right? And then the next time you want to decide what should be included in this top N, then you can use that information to optimize your cache, so to minimize the cache misses that you're saying. But you don't want to just cache miss and be like, forget it. You want to do like what the OS does, right? You go memory. If you don't find it in memory, it's in virtual memory. It's gonna swap out, and then you're gonna, you don't want to avoid like thrashing. But that's not impossible, right? You can have slightly slower prediction cache for infrequent predictions, but that are kind of important, and the client is willing to wait a little bit longer than the general latency timeout budget. But yeah, I've seen.
Musa, thanks a lot for that wonderful, insightful roadmap. One quick question that I didn't see, maybe it's embedded in one of those pictures, is how do you deal with an ensemble of models that actually have a kind of a pipeline that they might be dealing with both structured data and as well as unstructured data, and you might want to split up some prediction to go to the CPU and the other ones to go to the GPU because you're doing image inferences or you're doing segmentation in real time. How do you deal with that? Because there you actually have to deal with latency. Now you're actually transferring data to the memory GPU. How do you deal with that?
Correct. Yeah. The more generic way of saying it is I guess now they call them like model meshes, where you are not the only model in town. So you're it reminds me of like how insurance quotes used to be done, right? You're a broker, and the broker just sends, hey, who wants to insure this car? And then you have a bunch of insurance companies that are expected to respond, but they're competing with each other. So they're competing consumers. That's like in the Enterprise Integration Patterns book from Gregor Hope. You definitely want to structure it so that a lagger, someone that's not responding fast enough, you have a way to disqualify them so that you don't have to wait for slow models. For multi, so I gotta say in this low latency world, I haven't seen too much in the prediction request. that comes in, usually it's stripped down to its minimum. It's currently, you're right, like 2022, technology, you're gonna, the usual predictions that you're gonna get are gonna be super stripped down. So you're not dealing with, huge text, huge images, huge videos. You already, if you're getting any sort of those, you already pre-calculated like a feature vector for the video that you're showing, or you're really compressing the video to its minimum sort of features that are gonna come inside the ML gateway. So those are like the two techniques. So you have the competing consumers pattern, and you have the model mesh. I guess those are like two topics that fits with each other. And then in the low latency world, you definitely want to talk to your business stakeholders. Tell them the input features that we can ingest are gonna be, just one integer, please, kind of. But it is, yeah, today, right? It's just today. I don't know what the future is gonna bring, but.
All right, we got a couple questions over here.
Nice talk. I want to get your thoughts on technologies, like, in terms of Redis versus Cassandra versus Cockroach. What are the best ways? And also on the
So I did promise myself not to be technologically, not sell anybody. but I understand. Yeah, it's so. But in you have data warehouse, right? You have databases that are still storage-based, disk-based, or SSD-based that are optimized to have some nice lookup speed. And then you move into the how do you call them, the in-memory databases, and so that's for like the storage kind of thing. And then in the messaging part, same thing. Some messaging systems are optimized for throughput, right? That's something I didn't even talk about here, right? So like, usually they go together, right? You have a low latency system with a high throughput. Is very different from a low latency system with low throughput. These ideas can be used in both, but those are like the categories that you want to use when you're looking at a product, like the ones you mentioned, right? So data warehouse, disk-based, SSD-based database, and an in-memory store, and then you have messaging systems that are low latency messaging systems, and then throughput-based messaging systems. Those, in my mind, it's just it's just another way to think about it. Yeah.
Hi. Yeah. Thanks for the talk. A lot of these concepts seem to remind me a lot of just like microservices architectures in general. How would you say that, in the machine learning world, that might be different from, like Netflix does a lot of microservice architecture. They have Conductor, and these are big orchestration engines under the hood to optimize microservice latencies, right? How is ML just different?
Right. Yeah, it's amazing, right? 2022, we still don't have a good grasp of what I would argue for is that if you're managing a low latency system, you definitely want to keep pretty much everything that you rely on, every dependency inside your bounded context. You do not want to have excessive communication to another bounded context that a microservice architecture would provide you. So you are like, depending on a different team that might have a different release cadence, really like a different constraints for their job, for their tasks. You want to almost like replicate. If some data engineering team is helping you do feature engineering, feature transform, it's almost like you want to take snapshots inside your bounded context, so you don't have to rely on unnecessary dependencies. But it does have a lot to do with this microservice, because you're going to rely on a bunch of teams that are outside of your control. And even the networking, like if you're on a cloud provider, you definitely want to be not like an expert, but you want to know enough about regions, differences. You want to know about the co-location of your services, where are they going to live. Yeah, so that's what I would say about the microservice analogy to this challenges, I'd say.
All right, we have about literally 1 minute for questions, so I'm going to do the last one.
Hi. You touched on really quickly having the ability to kind of like log that a prediction event occurred to some like messaging service, but like that seems secondary to ultimately getting the prediction to the client in this case, that being the most important.
Right.
How do you, or how have you managed that conversation with the understanding if you're going to do logging in your application, there's some development cycle there versus saying to the client, maybe, client, you log this interaction in, you know, in terms of the payload and the response. How have you navigated those conversations, talking about, you know, how much faster it can make your development cycle or who that burden should be on?
Yeah, it is a great question. You know, the fact that you know you need an ML gateway that will orchestrate to some extent what's happening between you and the client is kind of, I guess, not advertised enough, that you don't realize that this ML gateway will be a critical source of future training data. So that's why I have like this little like link here where your ML gateway is whatever it gets, whatever prediction it's served, you know, it shoves it back to some messaging system for downstream consumers, which might end up in the events themselves. But deciding, I don't have a good answer on deciding, you know, which responsibility it is. My gut feeling is like, you know, the ML engineering team that's responsible for this, it's a product, right? You have inputs and you have exhaust. And if that exhaust is valuable, then it's part of your product. Then you wanna own it and provide it as hooks to debug, to analyze, to audit, to pass compliance. So I would keep it inside the bounded context again, but you know, depends on the case, right? Yeah. Cool. Thank you very much.
Thanks, everyone.